Good morning, everybody. We're going to start today with the next chapter. We're skipping chapter 12 and going to chapter 13. So this week we're going to Monday, Wednesday, and Tuesday. We're going to go through chapter 13. Then we'll do an experiment on Thursday and Friday. So we'll go through it on Thursday what we're doing. So this is the last week we're going to have lessons, and the next week we'll start to review for the final exam. So for today, we're on chapter 13.1. It's about gases. So one thing to know before we get started is the kinetic theory. And what this says is that when you increase the temperature of anything, whether it's a solid, liquid, or gas, the atoms go faster. So increasing temperature makes atoms move faster. And this is the basis of a few gas laws, which we'll talk about today. The first law is Boyle's law. Robert Boyle was an Irish chemist in 1627, and he discovered that the volume of a gas varies inversely with the pressure when temperature is held constant. So that's how we state this law in words. An equation is a lot simpler to use. So you'll see it more often like this. Let me write this out. Where pressure 1 over volume 2 equals pressure 2 over volume 1. And so Boyle's law looks at changing conditions. So you're looking at a gas that has one case. So in case 1, for example, let's say that the volume at the beginning is 4 liters. And the pressure, 210 kilopascals. Let me rewrite this so it's easier to see. Okay, so the original volume is 4 liters. Original pressure is 210 kilopascals. And then the gas changes to a new pressure and a new volume. So V2 now we're told is 2.5 liters. So this, we're just told this, we don't know this, we're just said this is what happens. And we want to find the new pressure. So in these problems, what will you'll be given everything except one term. So you have 4 variables in here, and you'll be given everything except one of the variables. You have to solve for it. So this is the initial conditions. The gas changes to a new condition, and that's what V2 and P2 represent, is the new condition. So all we need to do is plug these values in and solve. So we know that P1, 210 kilopascals. V2, 2.5 liters. And then we have on the right-hand side pressure 2, which is the unknown, over volume 1, which we're told was 4 liters. So we can cross multiply 2.5 times P2. Multiply that side. We get 4 liters times 210 kilopascals. Yes, Robert, you have a question?
Yeah, what are kilopascals?
Oh, that's a good question. It's a unit of measure of pressure. So we'll talk more about the different pressure units later, but for right now, just know that it measures pressure. And we'll say more about different units of pressure. PSI is the most common pressure unit. So if you check your tire pressure, it's usually 32 PSI. And PSI is pounds per square inch. So a pressure unit is usually a force over an area. As PSI equals pounds over square inches. And that's how much force is applied per square inch. And so for your tire, it's 32 PSI. There's 32 pounds of pressure per square inch of the tire. So that's a short answer as far as what pressure represents. And kilopascals is another kind of pressure unit, just like PSI. It's similar. And we'll go through, I should have done this before. I forgot we didn't go over pressure units. But we'll get to that later about, but for right now, just know that it's pressure. And whatever unit you start with for pressure, in this case is kilopascals, you'll end with that as well. So if you have kilopascals on this side, your pressure unit on this side will also be kilopascals. So at this point, let's solve for P2. Divide both sides by 2.5 liters. So we multiply and divide and solve for P2. And that gives us 340. Okay, and so it's unit pressure, and we can see right here, liters will cancel out. We just have kilopascals left. So our answer, 340 kilopascals for the new pressure. So the way Boyle arrived at this equation is through a series of experiments. He plotted volume over pressure on a graph, and he had a container of gas, and he changed the pressure. So originally we had a condition up here where it was one atmosphere. So another unit of pressure is atmosphere. And 1 atmosphere of pressure is the pressure you have right now around you. So it's atmospheric pressure. And so normally you're going to have 1 atmosphere of pressure if you're out in the open or in your house, because the atmosphere around you exerts a pressure. So P1 that he measured was at 1 atmosphere, and then volume 1. For his sample of gas, he had 10 liters of gas. Then he measured a new pressure and a new volume. So he raised the pressure to 2 atmospheres. And he found that the volume changed from 10 liters to 5 liters. So what he realized is that when he doubled the pressure, he halved the volume. And that's what he meant by inverse relationship. That whatever you do to one, in this case he doubles the pressure, you do the opposite to the other one. So if you double one, you divide the other one by 2. What he also realized is that if you take pressure 1 and V1 and multiply them, so you get 1 atmosphere times 10 liters, you get 10. And then if you take P2 and V2, multiply them, you also get 10. So the products of these are equal to each other. And so you realize that P1, V1 is equal to P2, V2. And that's no way you can write this equation. So the way that we saw it as P1 over V2 equals P2 over V1. That's just a rearrangement of this down here. So you could use either this or this as Boyle's law. They're the same thing. They just move them around. You can see if you cross multiplied this, you would get P2 V2 and P1 V1. So the way he explained it is like this, where if you take a piston, so the piston has some gas trapped in it. So a piston is found in your car engine. Basically, it's like a syringe. No, I can show you really fast. It's kind of like one of these where you have an enclosed area of gas and you have something that presses down on it and goes back and forth. So that's what a piston is. And so you have an area in here where gas is in this area, and the piston can increase the pressure of the gas by moving downward. So if you go from one volume to a new volume, and let's say that the piston moves down to right here, what happens to the gas? So over here, the gas molecules are closer together. They have less area to move through. And because of that, because there's less space for them to move through and they're squished together, they're in constant motion. They're about 1,000 miles per hour. They're bouncing all over the place. And if they have less room to move, they'll bounce off each other more and off the walls more. And pressure is really just equivalent to the force that the molecules apply to the wall of the container. Your tires stay inflated only because that the air molecules inside the tire are bouncing off the tire walls. If they stop moving, your tires would deflate. So it's the pressure that's exerted by the air molecules hitting the tire walls that makes the tires stay inflated. So if you decrease the volume, they have less room to move around. There's more pressure exerted on the wall of the container. So you can see right here, by decreasing volume, you've increased pressure. And one way to show this, let me show you a few demonstrations with this. So the syringe I showed you earlier, I'm going to use this to demonstrate Boyle's law. So I have a very small balloon I'm going to put inside the syringe. Okay, so you can change the pressure in here, and by changing the pressure, you can see the volume of the balloon change. So if I were to plug my finger over here, now there's nowhere for the gas to go. It's going to stay contained in here. If I were to push the syringe down, I am increasing the pressure of the container. Do you see how the balloon deflates when I press down on the syringe? And that's because I'm increasing the pressure of the gas. Now, if I do the opposite, put this down here really fast. If I were to instead move this out, now I'm decreasing the pressure. And you see how the balloon inflates? So as I decrease the pressure around the balloon inflates. If I increase the pressure, the balloon deflates. That might be a little hard to see on the video, but let me show you another thing that might be easier to see. And this shows you how the lungs work. I had this in my classroom earlier. You have your windpipe right here, goes to your two lungs, which are the purple and green balloons. This is your diaphragm down here. When your diaphragm moves outward, your lungs inflate. When it moves upward, your lungs deflate. Is that any easier to see in the video? It's hard for me to tell if that's clear or not. But this is Boyle's law at work, where if you decrease the volume by pressing up, then the pressure increases and your lungs deflate. If you pull down, you've increased the volume, then the pressure around the lungs is less and the lungs increase in size, they inflate. Okay, let's go into one more gas law today, and then we'll do a few questions to go over them. We looked at Boyle's law, and now we're looking at Charles' law. So Charles is his last name, Jacques Charles, in 1746. And what he found is that as temperature increases, volume also increases in a gas if you keep the pressure the same. So if you increase temperature and keep the same pressure, then the volume of the gas will increase. And this makes sense because at a higher temperature, the gas molecules are moving faster. And as they move faster, they hit the sides of the wall more often of the container, and that will increase their volume. Yes, Robert?
Does it increase at the same rate?
Oh, yeah, I mean, so you're asking if you double the temperature, do you double the volume?
Yeah.
Oh, that's a good question. Well, let's go through a few examples of that to see. If you were to look at, here, let me show you right here. Let's do that one. So let's look at what his law says as in an equation form. It says this, V1 over T1 equals V2 over T2. Okay, so let's try that. Let's say that for V1, you have a volume of 1 liter. Temperature, we'll say it's room temperature. Now, one thing about this is you have to use Kelvin. Did we go through converting to Kelvin in this course? No, we didn't. Okay, we'll have to go through that too. Because you couldn't use Fahrenheit or Celsius, you have to use Kelvin. And room temperature, it's about 298 Kelvin. And then for volume 2, so let's say we double the volume. So we go from 1 to 2 liters. And does the temperature also double? Well, let's see. So let's put in all the things that we know and solve for T2. Okay, so volume 1, 1 liter, over temperature 1, 298 Kelvin. On the right-hand side, you have 2 liters, solve for T2. So we'll cross multiply again. So we get 1 liter times T2 equals 298 times 2 liters. Okay, so on this side, it's just 1 times T2, so it just becomes T2. And then on the right-hand side, we would do 298 times 2. We get 596. And it's 596 twice of 298. It is, it's double. So the temperature did double when you doubled the volume. Let's go back for a second though and use Celsius instead. So if we were to put in Celsius instead, so for Celsius, that would be 25 degrees Celsius. So 298 Kelvin is the same thing as 25 degrees Celsius. And let's use that and go back and put everything in and see what happens. Okay, so we have V1 is 1 liter divided by T1, 25 degrees, equals V2, 2 liters, over T2. So cross multiply, we get 1 liter times T2 equals 25 degrees Celsius times 2 liters. So we'd multiply this out. Actually, that wasn't a good example because this time it actually does work, where we do actually get double temperature. It doesn't always, though. I wanted to show you that for Celsius, we don't always get double the temperature. In this case, it just worked out because we used 1 to begin with. It worked out that we did get double, but it doesn't always work that way where you get double. And that's what I wanted to show you, why we use Kelvin, but in this time it did get double. But for any of these equations right here, you can only use Kelvin and not Celsius. So let me go through how to convert between those before I go any further. If you want Kelvin and you're given Celsius, you would do the degrees in Celsius plus 273. So if you were given 25 degrees Celsius, you put that in here. Temperature in Kelvin would be 25 plus 273, 298 Kelvin. And the reason we use Kelvin is that it never actually gets to zero. 0 Kelvin is absolute zero. It's the coldest possible temperature in the universe, and we never actually reached it as far as we know. So we'll never encounter it. And let's look back at Charles's law and what it says. It says P1 over T1 equals P2 over T2. Could we put in 0 in the denominator? Well, you learn in math that you can't. You can't ever have 0 in the denominator. It's undefined. If you think about Fahrenheit and Celsius, we reach 0 degrees Celsius and Fahrenheit pretty easily. And it's very common to reach 0 degrees Kelvin, or 0 degrees Fahrenheit. And then 0 degrees Celsius even more common. 0 degrees Celsius is the freezing point of water. So if you get to 32 degrees Fahrenheit, that's 0 degrees Kelvin, or 0 degrees Celsius. So it's very common to reach 0 degrees Celsius and fairly common to reach 0 degrees Fahrenheit. But 0 Kelvin is never reached. And so we can be confident that we'll never have a 0 in the denominator if we use Kelvin. But if we use Fahrenheit or Celsius, it will become 0. And they'll go into negative values, which can't work either in this case, because we can't have negative pressure or negative volume for Boyle's law. Negative pressure and negative volume don't exist. And so those are two reasons why we can't use Celsius or Fahrenheit for these scales. Okay, let me demonstrate Charles's law really fast. Let me get this out. So I have a balloon in the freezer, and I wanted to show you what happens when you put the balloon in a hot temperature. Let me go ahead and move my computer out of the way so you can see this better. Okay. Move my computer so you can see that. So I have, this is boiling water right here. I have a balloon straight from the freezer that I'll put in here. So do you see how the balloon has already risen in volume? I don't know if the picture's very clear or not on there, but it was kind of shriveled from the freezer, and now it's expanding. And now it's around the walls of the beaker. And it's now touching the beaker walls, but while before it wasn't touching the walls of the beaker. And it's getting larger and larger in volume. Hopefully the picture shows that. And that demonstrates Charles's law, that the balloon was originally at about 0 degrees Fahrenheit in the freezer. And it went to a temperature about 212 degrees Fahrenheit above the boiling water. And by changing the temperature that much, you see a change in the volume of the balloon. And so that's because the gas molecules are moving faster with a higher temperature. And as they move faster, they hit the walls of the balloon harder and more frequently. And that will make the balloon increase in size. Let me show you also really fast a short video that, because it's hard for me to draw this one, but this video will demonstrate Charles's law a little bit better than I can by drawing it. Let me get this video pulled up for you. Okay, can you see the video? Go ahead and start that for you.
K. Very often, Charles' law is used to compare two situations, a before and an after. In that case, you can say V1 over T1 equals K and V2 over T2 equals K, so you can write Charles' law as V1 over T1 equals V2 over T2. Let's see an example. A hot air balloon has...
Actually, this is not where I wanted to show you. Let me go back. I wanted to find an illustration for you. Oh, here we go. This is what I wanted to show you.
Volume goes up. As the temperature of a gas goes down, its volume goes down. If you heat up a gas, it expands. The gas particles move faster, and they take up more space. Imagine a balloon that expands when gas particles bang against the sides. By expanding, that keeps the pressure constant. The faster the gas particles move, the more they will push on the sides of the balloon, expanding it. If, on the other hand, you cool the gas down, you put your balloon on ice, that slows the particles of gas down, so the balloon will contract. Jacques Charles is credited with this gas law relating temperature and volume, although he didn't publish it. He may have been too busy taking rides in hot air balloons. A colleague, Joseph Louis Gay-Lussac, published it, and very honorably gave Charles credit. Charles's law says that for a given...
Okay, so that's all I want to show you is just to illustrate what happens as the particles increase in movement with higher temperature. You can see that the walls of the container are under more pressure and they expand. And that's why we see an expansion with higher temperature. Let me go back to the whiteboard. Okay, so those are the two laws I wanted to show you today, how to use them. Charles's law is used the same way that we use Boyle's law. We're going to be given 3 of the 4 variables, and you solve for that one variable. For the test, it's good to have a note card with these down, and you can just refer to the note card of equations. So if you haven't already, I would get a note card of equations that we're going to be using in this chapter, because there's several equations which are not hard to use, but there are a lot that I don't want you to memorize. So I don't want you to memorize equations. Just write them down on a note card, and you can use them for homework and for the test. You have a question, Robert?
Yeah, so are we gonna have another test, or is this stuff just gonna be on the final?
We won't have a test over this, but yes, it will be on the final exam. So I'll pass out a study guide to you all this week with what you have to know for this chapter, but I won't have a test over this chapter, but it'll be on the final exam. Any other questions before we go on? Okay, for today, work on 2 questions, question 1 and then question 5. So this is on page 443. That's where question 1 is. And then go on to question 5. And that's on page 446.